Okay, so now I'll start to promise we're going to hear more about what you can do when you don't have a special starting curve, and about how the internship in Open was Luciano to have a similar inspiration and a similar time. So without further ado, this is Luciano Maino.
Hey, I would like to thank the organizers for giving me this opportunity. So today I'm going to present this paper, an attack on SIDH with arbitrary starting curve. This is joint work with Chloe and Martin. And so let's start without further ado. So, well, I mean, Bob already gave many explanation, many motivation for why we should focus on this problem. So one of the reasons why is that in 2016, the National Institute of Standard Technology launched a competition called Post-Quantum Network Standardization Competition. And amongst the protocols proposed for this competition, there were protocols based on isogenies. Usually, when isogeny-based protocols have many features. So first of all, isogenies have been intensively studied by mathematicians for years, so we know quite a lot about isogenies. And so we know how to work with isogenies. As Badr said, you can isogeny-based protocols enjoy short keys, but there is a drawback. Compared to other protocols, they are slower. So now I will give like my low-budget description of SIDH. It's not as fast as the previous one. So the only isogeny-based protocol in the competition so far is SIDH, which stands for Super Singular Isogeny Encapsulation. And SIDH is based on SIDH, which stands for Super Singular Isogeny Entanglement, which is like a key exchange. In a key exchange, you have two parties, Alice and Bob. So both parties agree on a starting curve, which is this one here. And Alice computes a secret walk in this graph and ends up in a point. Can't see it. Then Bob does the same, starting from the same starting curve. And then using some additional information, as Badr explained, Alice, starting from Bob's endpoint, repeats the same exact walk and ends up in on this curve, and Bob does the same in the other way. So if we want to break SIDH, what we are going to do is that we are going to retrieve the secret path that Alice or Bob, depends which side we want to break, build to compete to that in the graph. And then once you understand what's the secret path that, for instance, Alice used to compute the public key, then you can impersonate Alice and repeat the attack, repeat the computation. Okay, so actually the security of SIDH is based on this problem, which we describe like in a real formal way. So let P be a large prime, and let A and B be two large integers such that A, B, and P are pairwise co-prime. So also we are given two super singular elliptic curves, E0 and EA, and those curves are defined over P squared, and we know that those curves are connected by an degree A isogeny phi A, and also we are given the restriction of phi A to the B torsion group of A0. And then having all this information, we want to recover the secret isogeny in phi A. So it's worth noting that in this problem, E0 is not special in any way. So actually, the instance of the problem we try to attack is that we start from a generic elliptic curve starting point, and then we try to reconstruct secret isogeny. So as Bob already explained, this is there is already work to that, and that's like the attack that Bob and Thomas, the amazing attack that they published, and it's working really well. So okay, now let's move on to our attack. So phi A is the secret isogeny. Then to reconstruct phi A, and also we have like additional information on phi A. We have the image of the B torsion point of E0 under the isogeny phi A. What we do is that we compute a cofactor isogeny of degree F, and the degree of this cofactor isogeny will be like clear later on. And then what we try to do is try to guess this phi here. So I'm gonna explain how we did that. Maybe I will try to use the blackboard. So the information that we have so far are like, we have 2 points, PB, QB over E, and we know that PB and QB generate the B torsion group of E. Then we know the image phi B and phi QB. Then what we try to do is to reconstruct this endomorphism here, capital phi, which is given by the following coordinates. And I'm going to explain this notation. What do we mean with this endomorphism, with this notation? C phi A, CF A. C is an integer that we describe in the theorem that I will show later on. And actually it's easy to compute. Then the other component of capital phi, the secret endomorphism, is the dual of phi, that C phi minus 1. So to reconstruct the kernel of this endomorphism, this one is an endomorphism. Let me check my dash. Is an endomorphism of the elliptic product of E times EA. And the kernel of this endomorphism is given by PB C phi PB and A. QB phi QB. So it's worth noting that this data is public, so we know how to construct endomorphism. And so to break SIDH, I mean, to recover the secret isogeny phi A, we need to compute.
Use the other board.
This one?
Push the one at the back up.
Okay.
Space is no longer available.
So to recompute phi A, to recover phi A, we need to compute phi of PA and phi A of QA for some A and QA over E, such that the A torsion group of E is generated by QA. So to recover to evaluate phi A at PA, we do using the endomorphism. We evaluate the endomorphism that it's actually, that's something that we can actually compute on the point, on this pair of points. And using the matrix notation, we have that first component is given by V minus C by I of PA, and the other one and to compute the image of phi A, the image of QA under phi A, we use the pair QA and the identity on the other curve. And then we retrieve, it's not phi A, sorry, it's phi. Then we retrieve phi of PA up to a constant, which by our theorem is invertible modulo A. And so we do the same for phi of QA, and then we're done. So now I'm going to show like the theorem, and I mean this description of the attack kind of clear. Okay. So for the main theorem, we need 3 pairwise Cofactor integers f, a, and b, such that b is equal to f plus a. And here we have the description of c. So basically -1 over fa is equal to c squared modulo b. And then we have 2 supersingular elliptic curves connected by an fi isogeny. That's the reason why we need to compute this cofactor isogeny. And then we have the description, as I explained, the description of the kernel. And having this technical, request on the theorem, then we can retrieve this endomorphism. This endomorphism could be computed as a PE isogeny of principally polarized abelian surfaces, and the elliptic product is endowed with the product polarization. So we have all the information to reconstruct this endomorphism here and compute actually everything. So now let's move on to the complexity. Okay, so before finding some conditions on what we could use as like a cofactor isogeny, I need to give some details on the complexity of computing isogeny. So first of all, it's worth noting that we can compute isogenies via their kernels, and using various formula to compute an isogeny of prime degree L. The cost of that isogeny is O capital O L operations over the field of definition of the point that generates the kernel. Because we are computing the isogenies via their kernels. And the state of the art for large L is given by square root value formulae. And the complexity of these formulae are square root of L. That's the reason why it's called square root value. And the complexity is the operation over the field of definition of a point that generates the kernel. But we also need to highlight that doesn't work. This one is a memory complexity trade-off. So if L is too big, then might be difficult to store all the points and use the square root value formula. Okay, so now let's move on to our actual complexity. So rather than focusing on 2 generic parameters A and B, 2 generic coprime integers A and B, we assume that because that's the interesting case for SIDH, A is equal to power of a prime LA, and the same holds for B. And we can actually notice that F might not be smooth. So why do we need F to be smooth? Because I mean, when we compute, well, when we compute the, where is the image? When we compute the cofactor isogeny phi F, actually we compute that isogeny by a chain of prime degree isogenies. So if like we have that phi F is like a chain of isogenies of large prime degree, then attacking this way SIDH is not more efficient than trying to guess this phi A. That's the reason why we need to find some kind of smooth F. But if we use just F is equal to B minus A, there is no reason why F should be smooth. So to increase the pool of smooth Fs, we actually multiply B by some smooth E, and then we look for some smooth E such that F is smooth. But actually, we can do much better. Rather than just giving some kind of a little bit of freedom on E, we actually multiply B and A by some, so we multiply B by LB to the power of minus J, and we do the same for A. And then we look for some small I and J. And when we do that, this means that we actually, what we do implicitly, we try to guess the last I steps of the secret phi A isogeny, and then we apply to the theorem to the remaining parts. So in this way, we increase the potential, we increase the probability of having a smooth F. So the complexity of this attack will be divided in three main stages. The pre-computation step of E, I, J, and F. And this is something that we can do once and for all. So no matter which sorting curve that you use for like a set of primes, when you define like your public parameter, which relies on a certain prime, then we can compute once and for all this tuple. Then the other stage of our algorithm, study complexity of our attack, is the computation of the cofactor isogeny. And this one is what actually dominates the complexity of this attack. And then we need, once we take a guess of the last I steps of phi A, we need to repeat we need to apply the theorem for all the guesses that we try to do for the last I steps of phi A. Okay, so let's move on to the pre-computation. So as I said, the pre-computation of the tuple E, I, J, and F. So F determines the cost of computing the cofactor isogeny, phi F. So the cost of that computation is dominated by the biggest factor of F, the biggest prime factor of F. So if Q is a prime factor of F, then what we found experimentally is that the minimal field of definition for a Q torsion point has extension degree, which is roughly Q. So the problem is that when we try to compute phi F, we actually need to move to like big extension of FP squared. So this slows down a little bit our attack. And that's the reason why we need to be really careful on the choice of F. As regards J, we have no restrictions on J, because I mean, once we have the P torsion group to obtain the B times LB minus J torsion points, we can just multiply the B torsion points via L to the power of LB to the power of J. So I determines the number of guesses that we need to do for the last steps of the secret phi A. And also, as for E must be smooth, since to compute the endomorphism E times E prime, the endomorphism here, we must compute these isogenies here. And in our setting for the concrete attacks on SIDH, B is a power of 2, so we know how to compute 2 isogenies from and onto elliptic products. But as for E isogenies, E isogenies over elliptic products, we don't know that much, but we know how to compute E isogenies over Jacobians of genus 2 hyperelliptic curve. So what we can do to compute these isogenies, we move from an elliptic product to the Jacobian, and then on the Jacobian we compute E isogenies using known algorithm to compute E isogenies over Jacobians, and then to map from the Jacobian to the elliptic product, we use again a T2 isogenies. So that's the reason why we can actually generalize and increase the pool of smooth factors for our cofactor isogeny. So now let's move on to the computation of the cofactor isogeny, which is the most challenging step of our attack. So let phi-q be a prime factor of the cofactor isogeny phi-f, and actually, since En and En plus 1 are supersingular elliptic curves, we can guarantee that the codomain En plus 1 must be defined over fp squared, and we need this requirement because we need to store information on our algorithm during our attack. And actually, also when we compute the endomorphism on E times prime, we need to work over like this more over fp squared, otherwise the computation of the endomorphism itself is low. So this one is the first thing that we require. And also we require that for all AB torsion points on En, we require that the image of P under the isogeny phi-q should be defined over fp squared as well. So the methods to compute isogenies over fp, now let's list 2 methods that we describe in the paper to compute isogeny from irrational kernels defined over fp squared. So there is a subsection, there is a small section in the paper for square root values formula, which describes how to compute isogenies defined over fp squared starting from irrational kernels. And based on our heuristic, the minimal field of definition for a Q torsion point has extension degree Q. We can approximate the complexity of this square root values formula to tilde of Q to the power of 3 halves. And the other approach that we can actually follow is Coel's algorithm. So that this algorithm works from kernel polynomials, and the cost of this algorithm is given by Q squared. However, to retrieving kernel polynomials is not as trivial as it may seem. So one way to obtain kernel polynomials is factoring Q division polynomials. And the cost of factoring Q division polynomials is actually in polynomial time in Q and log P. So this one is actually still feasible. And now let's move on to a concrete instance that we gave in the paper. So Microsoft launched a challenge for these parameters here. A is equal to 3 to the power of 67, and B is equal to 2 to the power of 110. We found these values for I, E, and J. And this is the smooth degree of the isogeny, that the cofactor isogeny that we need to compute. And here we have the extension field degrees for all factors of F And so Q is a prime that divides F, and K is the minimal field, is the degree of the minimal field extension that over which Q torsion point is defined. So we think that for these parameters, the attack is still feasible, because I mean the field extensions are not so big. Now let's move on open problems. So these open problems are the open problems that we describe in the paper, and I will leave these open problems here on the slides. Anyway, discussing with many people, I mean lately after when we shared our attack, people told us that it's possible to, people like Luca and Theo, that we were talking like before the talk, told us that this attack is actually sub-exponential, has a sub-exponential complexity, and a way to improve this attack could be to solve the following problem. So given coprime integers A and B, we need to find smooth A and C and a small b, such that small a times capital A plus b times capital B is equal to C. So if we are able to find these values, actually, we can find more easily smooth values for F and actually make this attack even more variable. But overall, this attack is actually sub-exponential, and we do not require the knowledge of the endomorphism ring. So I guess that's all. Thanks for your attention.
I've got time for one very quick question, if anyone wants, but then we can discuss these things over our hour-long break afterwards. So. Anyone got a solution to this problem?
I've got a quick question.
Yeah.
So there's these like there's two variants of SIDH.
Yes.
Do you think these sort of methods could apply to that sort of problem?
Okay, that's a good question. I'm still thinking of, I mean, I'm already thinking about it, but this is just pure speculation, but I guess, yes, it's possible to apply kind of a variant to genus to SIDH.
Repeat question, please.
Oh, okay. So is it possible to apply same idea to the genus 2 version of SIDH? And the answer is that I believe so, but I don't actually have evidence for that. I just believe it.
Okay, on that note, can we move further questions for both Vasa and Luciano and Lola to break?